All right, cool. So hello everyone who's joining us online. So again, I'm the strategy director of WhiteBox. I co-founded it with Brian, and today I'm gonna give you a talk on, well, essentially it's a prelude to interpretability, right? So just to give everyone context about essentially like how these things work, and what our fellows have been doing in the past couple of months, right? So before we start, right? I originally gave this talk in Cebu 2 months ago, and if you're tuning in from there remotely, so almost none of this will be new to you, right? Oh, let me just set up my mic here. Okay, sure. All right, but so we've been busy since June, and we've learned quite a bit since then. So if you're one of the lucky ones, you should stick around and see the next chapter of this story, right? So I actually talked about interpretability last night, right, to a similar group of smart people like yourselves, and I will tell you what I told them. So our job in the next half hour is to retread what our fellows had to learn painstakingly in the last 5 months. Sounds impossible? Great. Let's begin. In 1839, right? So the Industrial Revolution was in full swing. So Queen Victoria was crowned 2 years prior, and with her rise and the rise of the British Empire came an era of gentleman science that was never seen before or since, right? So one particular gentleman scientist from the other side of the world, other side of the pond, right, was Theodore Schwann, right? Who, along with his many other accomplishments, gave us the word for metabolism and the 3 laws of robotics. Okay, well, no, I'm kidding. So it's actually this guy, right? So like some of you, I inhaled his books about robots, like going rogue as a kid. And it's a bit ironic that I'm now working on AI safety. But anyway, Schwann was responsible for extending the notion of biological cells to animals, right? So in particular, he made 3 claims about cells. The first one is that the cell is the unit of structure of living things, right? So and then the next one is that the cell retains a dual existence, as like a distinct entity, and also like what comprises organisms, right? So they're like the Lego blocks. And then the third claim is that cells form by free cell formation, which is more or less how crystals form, right? So this is not a biology seminar or something. So we're not actually we don't actually need to understand all of this, right? But the important thing about all this is that, well, before Schwann, right? So living matter was just clumps that do things, right? And then after this, it had parts, right? So universal parts that had their own set of rules and principles, and that everything you see from like the highest level can be fully accounted for by the myriad ways these parts combine and interact with each other. So in short, Schwann turned biology from an empirical science into a rigorous reductionist science, right? So we call this the central dogma of interpretability is kind of similar, right? So, and by the way, if you see this, right, so double question mark symbol, that means you can interrupt me with questions. So all right, we're good. All right, so let's continue. So we'll go over these one by one, but for now, notice what these claims are trying to do here, right? So we are trying to get from the inscrutable matrices inside neural networks and wringing the cells out of them, right? So just as Schwann did for biological cells 2 centuries ago. And well, the hope is that by identifying the actual universal parts of neural networks, we can also turn it into a rigorous scientific discipline. So yeah, I mean, that's a bold statement, right? But we're actually coming into this story while it's already underway, right? So let's go over some of the characters, right? So yeah, what is a feature, right? So defining this is hard and is why philosophers have jobs again, right? So for our purposes, we can think of a feature in the pragmatic sense that it is like, like one of the biggest AI labs in the world, Anthropic, does, right? So some detectable pattern in the data set that's complicated enough for a neural network to dedicate at least one neuron to it. So yeah, it's a lot of moving parts, but essentially, yeah, that's what it is. Like it's some pattern that's complicated enough for a neural network to dedicate one part of it to represent it or something, right? So yeah, here is what a feature actually looks like for an image classifier. So in particular, this is what you get if you try to maximize the activation of a particular neuron. And so we generally think of it as the answer to the question, right? So what is the neuron looking for, right? So in this case, this is supposedly a curve detecting feature, or well, it's actually multiple, implemented in multiple different places. But yeah, essentially in this model, right? So we have a dog snout feature, a cat ears feature, I don't know, front of the car feature, and so on. And some of the patterns are more difficult to give a label to, but for now, we'll stick with the, I guess, non-Lovecraftian bits of this horror story. So yeah, again, so double question mark. So any questions so far, even from the audience on Zoom? No? Okay, cool. Yeah, so all right, so that's one part of like claim one, right? So what about direction, right? So a direction in this context is basically some direction in the network's activation space, or in plain English, the possible outputs of a layer, right? So does this make sense? Well, yeah. So essentially, this is sort of like, this gives you an intuition of what that means, right? So you combine the activations of a bunch of neurons and out comes a vector. Wherever this vector is pointing at corresponds to some feature, right? So put in another way, when a network tries to identify dog snout in a very real sense, it points to some direction, in a 1,000-dimensional space, right? So you may have seen something similar in like, transformers where, if you add a vector in the woman direction to a vector in the king direction, and then subtract the vector in the man direction, right? So you get the vector for apparently queen, right? So this is not quite the same thing, right? But because directions, well, the directions we want to happen actually live in a different space. But yeah, we can leave the Y for, like actual transformer nerds out there. But yeah, in any case, this is sort of like what it looks like. And if you haven't seen this video, it's really good. This is a 3 blue 1 brown video on YouTube. So yeah, anyway, in any case, yeah, let's move on. So yeah, so now what is a circuit, right? So that's the next question. So a circuit is a set of features connected by weights. And when I say weights here, I mean the original weights in the network, right? So after all, right, so what we really care about is like decomposing actual live networks. And so we only let features interact with each other through what is actually there, right? And so with this, we're actually done, right? So, well, this is claim 2, right? So again, so features are connected by weights forming circuits. So, and then the third claim is that analogous features and circuits form across models and tasks. So yeah, here is everything in its generality. I realized I neglected to mention the first one, but yeah, essentially the first claim is that yeah, features are what we really want. Like they're the fundamental parts, right? And so they have directions, right? They correspond to directions, and then features build out circuits, and then these circuits are universal. With me so far? So yeah, any questions from the audience? What about people on Zoom? Yeah, so let me just. Okay, cool. So yeah, no questions so far. All right, cool. Yeah, so in any case, right, like going back to the story, right? So if all it takes to understand a model is to enumerate its features, then we can all go home, right? And then, we'd be out of a job, and yeah, none of this would happen, or would have happened. But well, fortunately, it turns out that the reality of the thing is stranger than we think. And well, remember how we defined a feature, right? So yeah, a feature again is a pattern that's important enough to correspond to at least one neuron. The keyword there is at least, right? So which means by default, we can expect to see that a feature is actually spread out over multiple neurons, right? So yeah, so our first example is, well, yeah, to see why this happens, right? So we consider a toy model with like a single neuron. So we have like one neuron, right? And then we want to represent 4 mutually exclusive features, right? So yeah, the neuron is binary, so either it fires or it doesn't. And then we have like an output vector, right? Which is a vector of probabilities of like, our 4 features A, B, C, and D, right? So the first case is, well, suppose N fires only with the first feature A, right? And then it fires uniformly for B, C, D, right? Like there's a uniform distribution over B, C, D, right? So what is the cross entropy loss? So this is the cross entropy loss for the people who haven't done like ML. But yeah, we essentially want to calculate this value, which is like a number that very roughly tells us how a model performs, right? So I'm sweeping under the rug a lot of nuances here, but generally, the lower this number, the better the performance, right? And yeah, I promise that this is the only formula in this entire talk. So we're just gonna use this and to like to make a point, right? So anywhere here, so P sub I is the true probability of the class I, which essentially it comes from the data set, right? And then Qi is the predicted probability of the class, which essentially comes from the model, right? And then log here is generally the natural log, but you can use any base you want. Sometimes people use base 2 so that it's in units of like bits. But yeah, we can just use natural log for this. But yeah, essentially, okay. So let's consider case 1, right? So again, case 1 is it fires for like A, and then it's a uniform it shouldn't fire for everything else, right? So yeah, so the neuron correctly predicts the token A, right? So the true probability distribution will be like 1, 0, 0, 0, right? Since again, the true token is A. And then the predicted probability distribution Q is also 1, 0, 0, 0. Does that make sense? Right? So yeah, and again, the reason for that is because the model predicts A with certainty, right? So therefore, the cross entropy loss for this, case is, well, 0. Right. So what happens if we get any of the remaining features? right? So the model predicts, again, a uniform distribution over tokens B, C, or D, right? And each of those will have a probability of 1/3, right? Because again, it's uniform, and there's three possible, three possibilities, right? So Q here is going to be 0, 1/3, 1/3, and 1/3, right? So since only one of BCD is like correct at any instance here, all right? So the true distribution for P for each non-case will be 0, 1, 0, 0, 0, 0, 1, 0, or 0, 0, 0, 1, which essentially means that, yeah, we have three cases which are analogous, right? So therefore, if we, again, so going back to this formula right here, right? So if we're doing this sum, essentially what we'll get is a loss of like log 3, right? So log of 3, and then yeah, if we add up all of that, right? So we get an overall loss of like 3/4 log 3, which roughly is like 0.8, right? So yeah. Anyway, so yeah, we're almost there. So you probably thought this was going to be a casual intro, didn't you? So, but stick around because there's a point to all this. Right. So what happens if we shoehorn two features into one neuron, right? So again, we have one neuron and 4 features, right? So suppose in this case, N fires for A and B, right? And then it's uniform for like C and D. Oh. So the question is, what is the cross entropy loss? So, you can turn the crank again and redo the calculations, and you should end up with the average loss or the overall loss being log of 2, which is around 0.7. So notice what happened there, right? So this loss is lower than the previous one, which was around 0.8, right? Which means if we actually train this network, this is the sort of behavior we get, right? So if we overload a neuron with more features, we get better performance by default. Now, yeah, this is bad, right? Because it turns out this kind of thing also happens if you try to scale this up for the kinds of data sets we want to train on, right? So, the number of features we want to find are usually just way, way more than the number of neurons we have. And so somewhere out there, someone has to we have to pack the features like sardines in a single neuron, right? And so, it's not. Okay. Anyway, so yeah, but yeah, just to be clear, right? So for the astute listeners out there, our example doesn't necessarily work if you use a different loss function. So for example, mean squared loss, right? But to my knowledge, no one really uses MSE or mean squared when training large language models. So yeah. Anyway, yeah, so this kind of thing where multiple features pack themselves into one neuron is called polysemanticity, right? And it is the first thing that you need to deal with when you want to interpret neural networks, right? So this is the thing we want. In other words, right, so we want to disentangle each neuron so that we can deal with one feature at a time, right? So one feature, one neuron. And of course, right, the major labs know this, right? So Anthropic in particular knows this, and they know it very well. And they've been hard at work trying to solve this problem, right? So the current most promising solution is known as a sparse autoencoder, or, well, SAEs, right? So let's break it down, right? So the autoencoder part here means like it's, well, and I'm hand waving a lot of things here, but yeah, it's a network with usually just one hidden layer, right? That's really, really wide. And its job is to transform its inputs so it fits some particular space, right? And then its job is to reconstruct those inputs from whatever that transformed representation is, right? So yeah, it's essentially, you have a lot of data, you put it in some space, and then it tries to reconstruct the original data, right, from that space. So yeah, and then the sparse here just means that, it's trained so that the activations are in some sense as spiky as possible, right? And as much as possible, they're concentrated in one neuron, right? So does that make sense, right? So again, one feature, one neuron is what we want, right? So when you train these SAEs, right? So you usually train them on the activations of like an LLM. And so you're sort of like letting the features breathe, right? Because there are more directions for them to occupy. And so one wild interpretation of this, and well, in WhiteBox, we're generally a fan of wild interpretations. Neural networks might actually be lower dimensional projections of much larger versions of themselves, right? So isn't that weird, right? So they might actually be simulating minds much larger than themselves in the name of efficiency, right? So yeah. So anyway, I told you we're already in the middle of the story here, right? So Anthropic has scaled these SAEs and found that they can actually generate entire sets of these features for production grade language models, right? So they're SAEs, which again, by virtue of training is functionally equivalent to the original model, have single features corresponding to as few neurons as possible, which means, well, are we done for? Is interpretability solved? Well, not really, right? So for one, you need really, really large SAEs to disentangle large language models. So it's somewhere on the order of like 8 to 500 times the number of the original neurons, right? And if you're already dealing with something like, I don't know, GPT-4, right, which has a lot of neurons and parameters, then you're looking at something that is definitely gonna be very expensive to train. So yeah, and then there's also a long tail of activations, right, that we still can't account for, right? So using SAEs, I mean, so for the largest models, right, so they tried the report, for the largest models that they tried in this report, right, so they still couldn't account for like up to 21% of the original model. Yeah, so yeah, which is essentially where we come in. So I like to think of WhiteBox as like a wizarding program for like aspiring magic users, right? So it just so happens that the magic is the magic system we happen to have is like, for some reason, if we put a bunch of GPUs in one spot and carve some runes onto them, right? So they start talking. And so as Brian mentioned earlier, our main thing is that we're running a fellowship to do cleanup in the aftermath of Anthropic's results. And the way we do that, right, is we gather some of the smartest 18 to 25-year-olds we know and give them the most intellectually stimulating environment possible, right? So in a very real sense, right, so we see ourselves as heirs to this ongoing intellectual tradition of just putting smart, earnest people in a room and then letting them talk to one another about, the pressing issues of society, right? And well, yeah, we also actually hold intellectual salons every Wednesday or Thursday. So lastly, I just want to echo what Brian covered earlier. So yeah, if you're interested in what we're doing, we'll be running a reading group like 1.5 months from now, where we'll discuss pertinent questions about what safety even means, right? And what it implies about how to align models to our values. So yeah, that's all. So hopefully we'll learn a thing or two from everyone else's presentations today. And thanks everyone for coming again.